work concerns the additively manufactured copper chromium zirconium alloy. In particular, this study concerns the improvement of mechanical properties by means of heat treatment. Why we studied copper chromium zirconium alloys? First of all, because this is one of the most successful copper alloys. This success is due to its high electrical conductivity and thermal conductivity, and in many environments, the good corrosion resistance. In this work, specimens were produced by means of additive manufacturing, and in particular by means of selective laser melting, by using the instrument shown in the slide. So here you can see the machine characteristics, and one of the main problems in producing additive manufactured copper alloys is that those alloys are characterized by very high thermal conductivity and high reflectivity. Those two characteristics generate defects like, for example, cavities or lack of fusion that will affect the mechanical properties of the alloy. Copper chromium zirconium powders have the nominal composition shown in the table. So this alloy, the powders used contain a small amount of chromium and zirconium necessary for age hardening. The powders used have a size varying over the range 15-45 micrometers. In this slide, you can see the parameters used for the printing process. So you can see the values of laser power, layer thickness, etch distance, and the optimal values of the process parameters were identified as the ones producing a volumetric energy density of about 260 joule per cubic millimeter. In this figure, you can see the two SAM micrographs showing the powder morphology. So as you can see, we have spherical particles. Their size is below 45 micrometers, but if you observe the micrographs in the figure, you can see also that those powders are characterized by the presence of a large number of satellites. The presence of those satellites can be explained considering that those powders are recycled during the printing process. Here you can see the analysis, the EDS analysis made on the powders. So you can see that those powders contain about 1% of chromium and 0.1% of zirconium. So we verified that the composition of the powders is the nominal one. Here you see the different specimens produced for the research. So we produce tensile and compression specimens. Those specimens have been designed on the ground of ASTM standard and on the ground of the requirement of the Hopkinson bar machine used for dynamic tests. Part of those specimens were initially heat treated, as suggested by the powder producer, at 560 degrees centigrade for 4-5 hours under nitrogen atmosphere. after producing the specimen have been cut, grinded, polished, etched with ferric chloride, and observed by using the optical microscope. As you can see from the two pictures, the two micrographs reported in the slide, the microstructure of the alloy is characterized by irregular grains. Those grains, as you can see here in the slide, are elongated in the direction of the heat removal. Moreover, we can notice, we can see arrows indicating the presence of lack of fusion, and we can see also, mainly on the left micrograph, the presence of cavities containing unmolten powders and or frozen droplets of the alloy. EDS analyses have been also performed on the specimen, so after the production process. So the EDS analysis reported in this slide show that the chromium concentration is about 60% in comparison with the one we found in the powders, and that the zirconium concentration is below the detectability limit of the instrument. So this consideration suggests that during the printing process, depending on the printing parameters used, we can evaporate part of the alloying elements. So this suggests also that if we change the production parameters, the printing parameters, so we can have different composition, we can obtain different composition of the alloy, and so different mechanical properties. If we compare the previous microstructure with this one, we can see that the microstructure is very different. The one you can see now in the slides shows the microstructure of a copper chromium zirconium alloy produced by means of traditional methods. This one was produced, so those pictures were taken after forging and aging. So you can see that here the grains are more regular. We can notice the presence of twins, and in the micrograph on the right part of the screen you can see also those small gray phases, which are chromium rich phases formed during the solidification of the alloy. Here we can have a look at the phase diagram showing that the quantity of alloying elements is so low because both zirconium and chromium have a very limited solubility inside copper. So after that, we performed aging treatment at 580 degrees centigrade, and we performed this aging treatment on two types of specimens. One was the as-built specimen. The other one was the same specimen but after solution annealing, performed at 980 degrees centigrade. So we can see that the blue line relative to the as-built sample show that the peak of the micro hardness, the weaker hardness, is reached very quickly. And then we have a sudden decrease of the hardness due to the overaging phenomena. While after solution annealing, we have again the formation of a hardness peak, but the hardness of the alloy is always much lower than the one that has not been subjected to the solution annealing. In order to explain the results we obtained, we performed X-ray analysis of the specimens. So the X-ray diffraction pattern of the S-built specimen shows only the peak of copper, while after solution annealing we can see that there is also a very small peak due to the formation of a zirconium-rich phase. So this suggests that after the production process, so in the S-built specimen, we have that because of the very high cooling rates during the additive manufacturing process, we have the formation of a supersaturated solution, while after solution annealing performed at high temperature, we produce diffusion of different elements and precipitation of zirconium and chromium rich phases. So in that way, zirconium and chromium are not available for forming the small nanoprecipitates, which are the ones that can effectively hinder the dislocation motion and increase the mechanical properties of the alloy. The following step of the research was to perform direct aging of the alloys. So aging performed directly on the S-built specimen at two different temperatures, 580 degrees centigrade and 450 degrees centigrade. The results are reported in the slide, so you can see that by lowering the aging treatment temperature, the micro hardness peak will be reached after a longer time because the diffusivity is lower, but it is possible to reach very high hardness value. This is due probably to the formation at lower temperature of nanoprecipitates. So that means that we have formation of nanoparticles able to hinder dislocation movement and able to increase the mechanical properties of the alloy. In conclusion, we can see that the additive manufacturing process of copper chromium zirconium alloys must be improved in order to reduce the formation of defects like cavities and lack of fusion, because they affect the mechanical behavior of the alloy. The results highlighted also that the high cooling rates involved in the production process allow to obtain in the S-built alloys the formation of a supersaturated solution that must be directly aged. And the results of the aging tests allowed to see that lower aging temperature determine the formation of smaller intermetallic particles that are able to increase the mechanical properties of the alloy. Thank you very much for your attention.